A very good day to everyone. So in today's class we will learn about a concept that is mixed concept. It is nothing but it has number one, the pressure at any particular depth is given as the atmospheric plus h times of rho times of g. This we have seen already. For example, if yes, we may have seen this in our fluid dynamics class. So if you have over here the container which has a liquid and it is open to the atmosphere itself, then at this particular point A, there is nothing but the pressure which is given as P naught plus h times of rho times of g. And if there is a gas over here, it is an ideal gas, then for isothermal process, then the product of the pressure and the volume will always remain a constant value. P1 V1, it must be equal to P2 V2. These two concepts, let us use it in a particular problem, right? And number three, the idea behind the barometer, right? If the barometer has a height of h, right, a mercury barometer, it has a height of h, then we can always write that the atmospheric pressure instead of h. Why? Because h we have already used. Let's use a different variable. Let's say that the barometer has a height of y, then it just means that the atmospheric pressure is y times of the density of the mercury multiplied by the g value. This is the meaning of the barometer height being equal to h. It has a separate concept also around it. The idea behind a barometer is that we invert a tube over here upside down within a mercury tub over here. It turns out that over here there is vacuum which will be formed over here. As we start to raise this particular tube outside of the liquid, the level of the liquid will, after a given point, it will start to fall over here and there will be vacuum that will be present. And over here, this height is nothing but equal to, let us say, some y value. By equating the pressures at these 2 points, so which 2 points? At these 2 points over here, that is the atmospheric pressure and the pressure due to the vacuum, which is 0, plus y column of density of the liquid, we arrive at a relation which is nothing but P naught is equal to how much? The vacuum's pressure, that is 0 itself, plus y multiplied by density of that barometric liquid. In this case, we are selecting that to be equal to mercury itself into g itself, right? Normally this comes out to be equal to 76 centimeter normally, but if it is not given, then you will just use y over here, right? These three concepts we'll be using for our problem over here, right? Suppose that there is the mercury over here, let us say, right? And we have over here our inverted tube over here. One end is closed and one end is open. Initially the pressure is nothing but atmospheric over here, right? And it is open over here inside also. There is atmospheric pressure only. And what we do in the next stage is that you immerse it over here. Immerse it within this particular liquid. And let's say that the liquid is also mercury, right? So what do you feel will happen? So this is the situation over here in this way, right? So needless to say, the situation will be in this way. The level of the mercury will not be the same over here within, because of the pressure from inside this particular gas. This level will be slightly below over here. It won't be at the same level, right? Maybe somewhere over here. Over here you would be having the gas, and in this way you would be having the situation over here, right? Here you have mercury throughout, right? So one equation you can now write. What is that? if the process over here is isothermal, whose process is isothermal? Of the gas which will be trapped over here, right? This particular gas undergoes an isothermal process, right? P1 V1 must be equal to P2 V2. Just when you were to bring it over here in contact, now it is cut off, now it is sealed off. So whatever is this particular PV must be equal to this particular PV now. Now the pressure would have changed. It would have actually increased because the volume is decreased. Earlier you had over here a length of how much? Earlier you had over here a length of, let us say, L. Now you do not have a length of L. You actually have a reduced value, right? How much is that? Let's say that it is nothing but some value. Let's give it a number. Let's call this as equal to x. X over here. Which one is x? Let us call this particular portion over here, this as equal to x. Yeah, that will be helpful. So one equation you can always write, that P naught multiplied by the volume. The volume over here is nothing but the area multiplied by the length itself, right? Initial P into initial volume, that is nothing but L into area. On this side, now the pressure is not P naught, now it's a different value. Let's call that as P1 into now the volume over here. How much is the volume there in that yellow colored region? Yes, it is actually L minus X multiplied by this area. If you cancel the area, you get P naught L as P1 multiplied by L minus of X, right? But what is P1? We'll go back and state that the pressure at A point can be found out by P naught plus H rho G value, right? So the pressure at this particular point over here, which point? This one over here, this A point, let us call this as. Can we say that that pressure is nothing but P naught, the pressure over here, plus this much of height into rho into G? Yes, we can say that, because over here you have continuously only the mercury which is present, right? So we can now state that PA is P naught plus this particular height over here is nothing but equal to, we need that particular distance data over here, right? So let us take that particular value. Maybe you may be given also over here, who knows, right? So let us take that for the time being, this particular distance to be equal to some value called as Z over here. We can't say that it is L minus X, because that would be length of the tube which is above A. So for now we'll just write it as P naught plus Z multiplied by density of the mercury multiplied by G itself, right? And this PA is the same as the pressure of the gas, because the pressure of the gas over here, it doesn't change much with height. It doesn't change. Only for very, very large changes, like top of the Everest, the bottom of the ocean, there it will top of the Everest and at the sea level, you'll find a large amount of difference in the pressure. Otherwise, generally within a room or even for few tens of meters, the pressure of air doesn't change. So therefore this P1 over here is the same as the pressure over here, the pressure at A. And now you just P1 is P naught plus Z into this particular value into G itself. You substitute the value over here, what do you get? P naught L, P1 is P naught plus Z density mercury into G into L minus of X. But suppose you are given the barometric height as equal to Y, then you substitute P naught as Y density of the mercury into G. Y mercury, Y, Y. And now you write for P naught on this side also, it is density of the y of the barometric height, mercury density, into G value, plus Z mercury density into G, and we are done. We are done. Just remove the rho and the G value. You get YL is equal to Y plus Z into L minus of X. Right? The same thing you can repeat even if it is taken to a very large depth over here. Let us say that this is the depth to which it has been taken, right? The same idea you can apply. You just have to go through the isothermal process. P naught multiplied by L times of A is equal to, now let's say that the present pressure over here is nothing but some other value. Let's call the P2 over here. The P2 is the same as the pressure over here, because you just have the same continuous liquid which is present inside this in the h by 3 length as well as outside. So over here also you have same density of the mercury, the same which permeates over here. In this region alone there is this air which is present over here, right? That's the only difference. So now we can write PV is constant for the gas, therefore it is P2 multiplied by its volume. What is its volume? If they have given you that this is nothing but equal to H itself, you just write H multiplied by A. Only for the yellow colored region, that much of length we want, right? Suppose that is not given as if that is not given, let us say, right, then what do you do? Well, you know that the total length of this tube is nothing but equal to how much? L. So what will be the volume which is present inside that yellow region? Yes, you guessed it right. It is L minus of H by 3 multiplied by A. That's all. This is very simple, right? And what do you do for this P2 now? What do you write this as? The pressure of the gas over here, because it is the air only, is the same as the pressure over here, which is the same as the pressure over here. And what is the pressure over here? It is P naught plus how much? You go all the way to this particular point. But what is this particular height over here? Is it not L minus H by 3? Yes. So you can write over here, if this is your L minus of H by 3, then the P2 becomes P naught plus H by 2 for how much of height? For this much of height, plus this particular H rho G value. So you can write P naught plus H by 2 density of the mercury into G value. As long as it is mercury, if it is water, then you use the water's density, right? And plus L minus H by 3 into density of the mercury into G value. It's very, very simple. Now just substitute this back over here in the place of P2 and you solve over here. And remember, barometric height, if it is given, you just write Y into density of the mercury into G value, if the barometric height is given as Y. Idea is clear, gentlemen. No doubts on that. Yes or no? I hope it is extremely useful to you guys. That's it.